Hello students, this is Mr. Yao. Today we are going to continue to work with trig identities. As you may notice last time, we have been working with some fractions, so let's first review some number fractions. For A, 2/3 over 4 over 15. You have two different ways to deal with this. One, you can choose to treat it as division, so basically divided by 4 over 15. That means you can multiply by its reciprocal, and then that's going to give you 30 over 12. So you can choose to do that and then simplify the fraction to give you a divide the top and the bottom by a 6. That's going to give you a 5 over 2. That's one way. Or the second way is I'm going to keep this, and you may notice the denominators are 3 and 15. Their common denominator would be a 15. So I'm going to multiply the top and the bottom by a 15. That's going to be gone. The top, that's going to become a 5. So it's going to be a 10 over 4, which is also going to be simplified to 5 over 2. So that's two different ways. And when you're simplifying fractions, you can choose to multiply them and then simplify the whole thing, or you can choose to cross cancel. Either way. So for B, let's try the common denominator again. Common denominator is going to be a 35. So multiply the top and the bottom by a 35. That is gone. That is 7. Going to become 28 over 4, which is simplified to be a 7. For C, multiply the top and the bottom by a 5. The top is a 2, and the bottom is a 3. For D, you got to be careful with this one. The bottom is actually a 2 over 1. That's how the fraction is. So the denominators are a 2 and a 1. Multiply the top and the bottom by the common denominator, which is 2. That is gone. The top becomes a 1. The bottom is a 2 times a 2, which is a 4. If you actually choose to do it the other way, it's going to confirm. 1/2 times the reciprocal of 2 over 1 is 1 over 2, which becomes 1/4. That works as well. The reason for these fraction practices is because when we do trig identities, this a little bit in this lesson and more in next lesson, we are going to work more with these fraction form of trig identities. Now let's recap on what we have learned. Pythagorean identity, sine squared plus cosine squared equals 1. In this lesson, we are going to do a bit more with this Pythagorean identity, because we can actually subtract the cosine square on both sides or subtract the sine square on both sides. That's going to give us sine squared equals 1 minus cosine squared. That's when we subtract the cosine square on both sides. Or cosine squared equals 1 minus sine squared. That's when we actually subtract the sine square on both sides. Of course, we have also learned quotient identity. Tangent is sine over cosine, and cotangent is cosine over sine. Now let's get into the examples. Today's lesson, we are going to combine these identities together and also learn how to do proofs using them. Here are a few helpful tips. First one, you can either start from the left side and prove to get to the right side, or you can start from the right side and prove to get to the left side. We typically start with a more complicated side. Bullet point 2, if you really don't know where to start, always try to change everything into a sine or cosine first, and then proceed from there. Lastly, don't forget, for fractions, you can start with a common denominator or cross multiply. Or in other words, cross multiply is actually a cross cancel. Remember, there may also be factoring and or distribution involved. We're going to work more with that in the next lesson, just a little bit in this lesson. Now let's have a look at some examples. First, we are going to simplify things. Cosine squared plus tangent squared times cosine squared. Well, in this case, there are kind of two different ways. First, you can choose to factor out the cosine square, or you can choose to just rewrite everything. So this is, of course, the left-hand side. So cosine squared. Tangent is sine over cosine. So sine squared over cosine squared times a cosine squared. That is gone. So we have cosine squared plus sine squared. Now, that is our Pythagorean identity. So this whole thing simplifies to be a 1. Example 2. This time we have nothing that we can rewrite into, so we have to directly work with it. This is sine theta squared. This is also sine theta squared. So this question is now very similar to, say, like x minus yx. Both parts have the x, so I can factor that out. I can factor out the sine theta squared. Just like here, I can factor out the x. That's going to become 1 minus y. Same thing here. When you factor out the sine theta squared, you are left with a 1 in the first term. And you're left with a cosine theta squared in the second term. Now, let's continue. Sine theta squared doesn't change. 1 minus cosine theta squared. You do need to notice that. That will become sine theta squared. By our Pythagorean identity, like a little change of Pythagorean identity, sine theta squared times sine theta squared is going to become sine theta to the 4th power. That's example 2. Moving on, now it's time to prove stuff. Clearly, the left side looks more complicated than the right side, so we are going to start on the left-hand side. So we're going to write LHSS, left-hand side, to indicate we are starting on the left side. Cotangent becomes cosine over sine. Cosecant becomes 1 over sine. So I just started doing that because there's kind of nothing else I can do. So I might as well change them all into sine and cosine, see what I can do there. Both denominators are sine, so I'm going to multiply the top and the bottom by a sine theta. You see, that is the fractions that we worked with. Sine is gone, so we are left with a cosine theta on the top and a 1 on the bottom. That is cosine theta, which is my right-hand side. So I did just prove it. That's example 3. Example 4. Left side looks simpler than the right side. So this time I'm going to start on the right-hand side first. Right-hand side is going to be sine theta over cosine theta, the whole thing over a sine theta. Or I can rewrite it as sine theta over 1. That means my common denominator is going to be a cosine theta. That is canceled. On the bottom, I don't have anything I can cancel, so I'm going to be left with sine theta over sine theta times cosine theta. Now, you can only cancel when things are being multiplied. You can't cancel anything that's adding or subtracting. And in this case, we have sine times cosine, so I can cancel the sine, left with a 1 on the top and a cosine on the bottom. 1 over cosine is secant. That happens to be my left-hand side, and again, I just proved it. That's example 4. Let's keep on going to a couple more. Example 5. Left-hand side look a bit more complicated, so let's start with that. Left-hand side equals 1 minus cosine squared. Now you really do need to notice that. That is sine squared over cosine squared. Well, sine squared over cosine squared is basically the step you don't have to write, but I'm just going to show you, to be clear, is the same as sine over cosine, then squared. That is tangent squared, which is my right-hand side. So we're done with example 5. Next, example 6. Start on the left-hand side because that's a bit more complicated. 1 plus, well, there's kind of nothing I can work with, so I'm just going to rewrite everything into sine and cosine. Tangent is sine squared over cosine squared. That 1 is basically 1 over 1. So that means my denominators are 1 and cosine theta squared. So I can choose to get a common denominator, which is cosine squared. In order for the 1 over 1 to be cosine squared on the bottom, I need to multiply the top and the bottom by a cosine theta squared. So now the top is cosine theta squared. The other one is the sine theta squared. Oh, voila, we have cosine squared plus sine squared. That is 1 over cosine squared, which basically is 1 over cosine, then square the whole thing. And that is secant squared, which is my right-hand side. So I am done again. That's example 6. Next, example 7. So this time, left-hand side looks a bit more complicated. Let's start with that. I'm going to rewrite everything into sine and cosine. And in case you haven't noticed, secant is 1 over cosine. And if I have another one on the top, basically by the reciprocal identity, this whole thing is cosine theta squared. And 1 over cosecant is sine, so that becomes sine theta squared. Look at that. Cosine squared plus sine squared by Pythagorean identity, that is a 1, and that is my right-hand side. Proved. That's example 7. Next, example 8. That left-hand side looked quite a bit more complicated. So I'm going to start with the left-hand side. You kind of have a couple different ways to deal with this question. So first, if you're like, I have no idea how to do this, well, write them into sine and cosine. So let me label them. The first method, sine theta over cosine theta, because cotangent is cosine over sine. Then times a cotangent again is cosine over sine, plus tangent is sine over cosine. Next, you can choose to get a common denominator inside the parentheses. So this is going to give you cosine theta over sine theta times the common denominator of a sine and cosine. So here's an example. It's basically the same as 3 over 5 plus 5 over 3. You do need a common denominator, which is both, which is 15. So in this case, my common denominator is sine theta cosine theta. And in order for the first term become sine and cosine, I need to multiply the top and the bottom by a cosine. In order for the second term becomes the common denominator, I need to multiply the top and the bottom by a sine. In this case, cosine times cosine becomes cosine squared. Sine times cosine, sine times sine becomes sine squared. And when you look at that, my top is actually a 1. So next, I have cosine over sine times 1 over sine cosine. My cosine would cancel, so I basically have a 1 over sine squared. That is cosecant squared. That is my right-hand side. And that's the first method. There are 2 more methods, but I'm just gonna show 1 more. So let's have a look at another one. You can choose to, after I get the first step, let's start with the first step again, cosine over sine, and you have cosine over sine plus sine over cosine. After that first step, you have parentheses, so you can actually choose to distribute. And the third method is basically without changing them into sine and cosine, distribute right away. So you can also choose to, just do this right away. And notice that cotangent and times tangent is going to give you a 1. So in this case, cosine times cosine on the top is cosine squared. Sine times sine on the bottom is sine squared. Cosine over sine times sine over cosine becomes a 1, or 1 over 1. That means I can change them into the common denominator, which is sine squared. The first term doesn't change, but the second term, if I want to change it into a sine square on the bottom, I need to multiply the top and the bottom by a sine squared. So another sine squared. That means my top is actually just a 1. So 1 over sine squared is cosecant squared. And that is my right-hand side. That is proved. So that's 2 different ways. And of course, like I said, if you choose to distribute at the very beginning without changing them into cosine or sine, that is going to be a third method. Kind of work the same way as the second one. That's example 8. Next, example 9. Let's start from the left-hand side. 1 minus 2 times sine squared. And the right-hand side kind of looks similar, so I'm just going to start on the left side. First, there's kind of nothing I can do. I do not know, with the 2 and everything, I have no idea what I can do. But at least I know there's one identity I can choose to use for the sine squared. So I'm just going to use that. Sine squared is the same as 1 minus cosine squared. The other reason why I use this is the right-hand side, I notice I have cosine squared. So that means no matter what, I need some cosine squares. That's why I'm going to rewrite the sine squared using the Pythagorean identity into 1 minus cosine squared. Now it's time to distribute. So 1 minus, the 2 times 1 is a 2. The negative 2 times a negative cosine squared is going to be a positive 2 cosine theta squared. 1 minus 2 is a negative 1 plus 2 cosine theta squared. Well, actually, you look at that. I just need to flip the order. So put 2 cosine squared in the front, minus 1. That is my right-hand side. That is done. If you choose to start on the right-hand side, it's the same idea. You are going to rewrite the cosine squared. You are going to rewrite this as 1 minus sine squared. And then do your distribution, and that would give you the left-hand side. That's example 9. Next, example 10. Left-hand side is more complicated. Let's start there. I'm going to rewrite everything using sine and cosine, since there's not much I can do out. So the bottom is also 1 minus sine. This is basically cosine over 1. So that means my common denominator in this case would be a sine. So I'm going to multiply the top and the bottom by a sine. Or in other words, I'm going to multiply everything by a sine. So that is gone. I have a 1 on the top, and then minus the cosine times sine. And, oh, actually, I wrote it wrong. I started wrong. So let's start over. Is actually not sine there. Is actually going to be a cosine there. My secant is actually cosine theta. So that means my common denominator is actually going to be a cosine. So times everything by a cosine. There we go. So that is gone. Then I have 1 minus cosine square on the top. The bottom is also gone. That's a 1. Basically, I have 1 minus cosine square left. And 1 minus cosine square, by now you should know it, it is sine square. That is my right-hand side. I just proved example 10. That is everything for 5.9b. Thank you.